Now the furanose form is where you make a 5-membered ring. So it just means you're going to close the ring smaller. So sometimes it's because you have less carbons, or sometimes it means you use a certain OH group. So for example, here we have, instead of a C double bond O on the end, we have it 1 carbon in. So that's going to already shorten my ring size. So that means this OH group attacks here, and then that makes it into a 5-membered ring instead of 6. And notice that the idea of up and down is preserved. This is on the left, so that's up. And then this is on the right, so that's down. And then this is the anomeric carbon, so it is used to close the ring. Okay, so that's how we get a furanose ring, which means a 5-membered ring. And this is also an example of a ketose, and a ketose closing gives you sort of the symmetrical hemiacetal, except the OH groups aren't symmetrical. But it gives you a O in the center, and then it gives you 2 carbons on the left, 2 carbons on the right, and the CH2OH, CH2OH, and you can have alpha or beta here as well. So some reactions of monosaccharides, since they're all hydroxyl-containing compounds, we have lots of hydroxyl groups. This is very much just alcohol chemistry at this point. So carbohydrates are polyalcohols. They have lots of OH groups on them. They also have, aldehydes or ketone groups as well. So carbonyl group. So here we have OH groups right here. So any of those are susceptible to reagents which modify alcohols. So if I have acetic anhydride, that looks like this. And we've used this reagent before. I think you can see how I could do nucleophilic substitution on that. So we've learned how to do this kind of thing, right? And so that means that at each of these oxygens, you're going to get an acetyl group, which looks like that. So if I may, I'll just show you. So that would be an O, C double bond O, CH3. And that would be at all of these OH groups, because they're all OH groups. Another reaction is if I had methyl iodide. So methyl iodide is really good for SN2 kind of reactions where I have partial positive, partial negative. So a nucleophile can attack the CH3 and let go of the I. So that's very common, and we saw this in the amines chapter, that we had a lot of methylation, especially in a basic solution like with silver oxide. This oxygen becomes more negatively charged, and then it attacks the methyl group. Again, it reacts at all the OH groups because they're all susceptible for methylation. Now, one difference is where we have this reaction, methanol in acid, we actually have a difference in which OH groups react. And if you look at this reaction, notice that only this one reacts, but the rest of the OH groups are left alone. So why do you guys think that is? This is a reaction from this quarter, actually. Well, if you guys remember, this is a hemiacetal, so that's the hint. And a hemiacetal is where you have an OH group and an OR group. This is an R group out here. Let's say all of this is R. Okay, so that means that if I have acid, I might protonate it there. This could potentially open up. So maybe one way it could do that is, there's lots of different ways you could show this. This might open up like this. And once you have that, then you can have attack by methanol. So the idea here is that the OH group would be in the back somewhere, okay? And then you would have some kind of C double bond O H plus, okay? So we have something like this. And then you have the methanol that can come and attack. And then eventually we have the OH leave as water, and we have a methoxy group from the methanol. And it can attack on the top or the bottom, because the carbonyl group can be up or down, and that leads to the alpha and beta forms. The fact that I'm getting a mixture of alpha and beta, that tells me that, oh, there's an open chain and then it closed up again. And so that's how you get alpha and beta. Okay, so this is the only one where only one of the OH groups reacts, because it's a hemiacetal going to an acetal. So it only happens at that one anomeric carbon. Okay, so these are just some practice problems where you use one of these sugars and you practice doing all three of these reactions to it. Okay, and so this is practice with acetic anhydride, this is practice with the methyl iodide. And now let's take a look at some other kind of reactions that could take place with sugars. These are organic chemistry reactions. So taking a look at the reactions here, we have just regular organic chemistry going on. So we have sugar on the left. This is a glucopyranose, six-membered ring. And notice it's a hemiacetal, so the anomeric carbon has an OH group. So that means that we're able to convert this into an aldehyde. So there's an equilibrium established where some of it is in its open form, aldehyde. This aldehyde can react like any aldehydes we've learned this quarter, can get reduced to an alcohol. So we usually use sodium borohydride with water, or you could use LAH as we've been doing as well, but it's a little more harsh to use LAH. Now, a sugar is an aldehyde here, in this case, not a ketose, but a hexose in this case. So it can get reduced to an alcohol, but a sugar, which is an aldehyde in its open form, can also be oxidized because aldehyde can go either way. So here's an example of an aldehyde getting oxidized. And so we call the sugar a reducing agent or a reducing sugar. And this is an example of glucopyranose again, so all based on glucose. The idea is an aldehyde actually can be reduced or can be oxidized. You just need an oxidizing agent to do that. We use two different kinds of oxidizing agents for sugars. For this chapter, we're using nitric acid and water and heat. And then another one that you might see is bromine right here, bromine and water. That's another kind of oxidizing agent that will do this reaction. All right. So in order for this to work, though, you have to get it in its open chain first. And if you guys think back to how an acetal converts back to an aldehyde, it does something like this. I think you guys see, right? So this is an H here, and that's the key to making an aldehyde. So this is an hemiacetal, and hemiacetals have that ability to turn into an aldehyde because this O double bond, C double bond O, can be deprotonated and made into a carbonyl group. Same thing here, this is a hemiacetal. This can become a carbonyl group because I could just deprotonate the H later. But if I have an acetal, then this is not going to be able to be neutralized. See, this carbon's going to be OCH3, and then there's no way to deprotonate that, so it's not going to be able to react as easily. So this is not going to convert into its open chain form, because this is an acetal. And what we really need for reducing sugars is its ability to open up into an aldehyde. So it has to be a hemiacetal for this to work. So reducing sugars have to be in either hemiacetal, cyclic form that can open to the open chain, or already be in its open chain. All right, so here, this is an acetal or a cyclic hemiacetal. This here has an OH group, so this is definitely hemiacetal. And so this means that this is a reducing sugar. So I'll write yes, and for this one I'll write no. All right, and so why don't you take the last one? Is the last one a reducing sugar? I'm going to say that even though these are all methylated, I would say that it is a reducing sugar because you still have the ability to form an aldehyde, and that aldehyde is going to have an ability to oxidize, even though these other groups are methylated. Okay, so I'm going to say yes. It's a reducing sugar as well. All right, last part of this chapter is looking at linking monosaccharides together into disaccharides. So monosaccharides are polymers. They can link together like Legos. Okay, so if you have one sugar here and another sugar here, this is glucose. Okay, one glucose linked to another glucose. Notice the linkage is right here between those two sugars. It's the OH at the fourth carbon of one glucose with the alpha OH group of another glucose behind it. So we've got two sugars linked together. This is called an alpha-1,4 glycoside, so glycosidic bond. Glycosidic bonds are what link sugars together. Usually when two sugars come together, you release water. One of the OH groups leaves as water, and you have this ether instead. Okay, let's break this apart. This is called 1,4 because it's the carbon 1 and a carbon 4 linked together. Alpha because this OH group is down. And that's basically it. Okay, so maltose, that's a hydrolysis of starch. If I take a long chain of glucose and I hydrolyze it, it breaks it down into smaller pieces. Maltose is one of those sugars with a 2 glucose unit bonded together. Now cellulose we can't digest. Cellulose has a different kind of bond that enzymes cannot digest for us. They can't break those. So the enzymes that break these apart do not break these apart. So the only difference though is that this is alpha, whereas this is beta. So in cellulose, it turns out they're beta linkages that our enzymes aren't good at chopping down. Okay, so if I could chop this down, I'd have glucose, but our bodies aren't great at doing that. All right, so Cellobiose, we can try reacting Cellobiose with these different compounds. And I think you will notice that Cellobiose is 2 sugar units, so we have to evaluate each one. This sugar unit here is an acetal at this carbon. So I'm not going to be able to open up the chain here. But this part here is a hemiacetal, so I can open up the chain there. So just keep in mind when you open the chain, you'll be able to open it here, and then you can react it with these reagents. So what will I get? For the first one, part A, I'll get the same sugar, but I'm not going to be able to break it open until this step here. So here's where my open chain occurs, right here. Okay, so you guys following that? So right here is my aldehyde. And so from there, then all I have to do is, so first I'm going to protonate that to make it an OH. And then this part here is going to get reduced because this is a reducing agent. And if you don't remember that, you can just scroll back up here. That's this reaction here. Aldehyde goes to alcohol. Okay, so I'm just going to change this part then to an alcohol. All right, so that's how you do these problems. Okay, using the same idea for part B. For part B, I would take the same molecule, but I'm going to oxidize it using Br2H2O. So that means I'm going to change this group here to a carboxylic acid. Because remember, I started with the aldehyde, and then I reduced it to an alcohol, and now in part B, I'm oxidizing it to a carboxylic acid. In part C, I'm basically making a acetal. So I'm going to change this OH group to an OCH3 group. That's what part C does. And part D is I'm going to change all of the OH groups into acetylated OH groups because I'm reacting with acetic anhydride. And then the OH groups all attack here, right? And I let go of that. So for part D, which I'll do in a different color, here's part D. All of these are going to be OAC, 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 all acetyl groups right here. So that's the basic idea of practicing these. Finally, a couple more sugars just for interest. Lactose, you often hear about people being lactose intolerant. So that's where our enzymes, we don't have enough lactase enzyme perhaps to break down lactose. So you get bloated and terrible consequences. All right, but not life-threatening or anything, just uncomfortable usually. So basically that's a galactose monosaccharide linked to a glucose. And it's a beta 1,4. So this is beta pointing up. And it's a 1,4 linkage. And then this is the beta pyranose form that they just happen to be showing you. Okay, so that's lactose. With sucrose, which is table sugar, it turns out being glucose and a fructose. So when you break that bond, you end up with these individual sugars, which we can do quite easily. And when we have table sugar, for example, this is an example of a 1,2 glycoside. And this one happens to look like an alpha 1,2. Now, a couple of interesting things is people with arthritis, they usually have prescribed from their doctors chondroitin sulfate or glucosamine. So maybe you've heard about those supplements in the health food stores or in the pharmacy section of grocery store. So often these are based on sugars. They are glucosamines, means that they are sugars linked to proteins. So they're actually glycoproteins, which are combinations of sugars and proteins or amino acids. So these are really useful for building cartilage, they say. Although people with arthritis might tell you it doesn't work that well. Another one is glycoproteins are also used for cell surface recognition, and this is very useful for understanding blood types. So for blood type, about being A positive or O, or all these different blood types, AB. That's due to a kind of signature on your blood cell surfaces, which is based on glycoprotein composition. So you could actually see different kinds of sugars and proteins linked together to give you a unique profile that results in compatibility or not between blood cells. It's really important to make sure when you get a blood transfusion that you have the right, that you have a compatible blood transfusion. And a couple of other things, lactose intolerance, it's usually due to not having enough lactase enzyme to break down lactose. There's actually a more serious disease called galactosemia. That's where galactose cannot be broken down or metabolized. And, lactose intolerance, people with that can be very uncomfortable. But galactosemia, that's actually very serious. It could cause death even. So it's very important that babies, for example, are screened for that. That's where you can't digest galactose, and that's very common in milk. So it's very important to test babies for that, especially since that's all they can drink. So that's just a quick rundown of carbohydrates. I hope you guys feel more comfortable looking at these structures and noting, how they're linked together. These are two separate monosaccharides. This is an beta linkage here. This is at the 1, 2, 3, 4, 4, 1, 4. Beta linkage, for example. So I hope you can sort of see that now, and the significance of all these OH groups, and the fact that this is a hemiacetal tells us this is also a reducing sugar. So that's very useful to know these things as well. Particularly in the old days, when all we had were chemical tests, often reducing sugars could tell us what sugars it was possible to be. Reducing sugars were often tested for by looking at how they reacted with copper, for example. Copper 2 plus could react with a reducing sugar to get oxidized from its blue form, copper 2 plus, to its copper 1 plus oxidation state, which is a red-orange color. So this is called Benedict's test, and it's very helpful for identifying whether you have a reducing sugar or not. Back in the day when you didn't really know structure, it really helped to narrow things down. And many of you know that one test for diabetes, for example, is to test for glucose. So just knowing what sugars you have can be very important in detecting diseases. Also, we talked about starch. Starch is a chain of glucose molecules, which are alpha 1,4 glycosidic linkages. Amylose or amylase is an enzyme in our saliva, for example, that can break down these starches. So if you just take a piece of bread and just hold it in your mouth for a while and just let it soak in, you'll start to taste the sweetness from just the natural enzymes in your saliva breaking that down. Cellulose, of course, is a beta 1,4 linkage, so we talked about how your saliva or your amylase cannot break that down. Some of you might be interested in sugar substitutes as well. So stevia is a really common one, and it's natural, so it comes from a stevia plant. So a lot of people like it because it's natural. And you can see there are some monosaccharides here linked together with this compound right there. Some of you are very familiar with equal or aspartame, and that's another kind of sweetener, but notice its structure has nothing to do with sugars. In fact, aspartame is diamino acid. So we're going to learn about amino acids in the next section, but it's a modified amino acid over here and another one over here. So we'll learn about that later, but it tends to bind our receptors in a way that triggers sweetness. So just thought you might be interested that aspartame actually does not in any way look like a sugar. And then some of you know about sucralose or Splenda. And sucralose here's sucrose, which is just OH groups here everywhere. And so we talked about how it's glucose and fructose linked together. Splenda or sucralose replaces some of the OH groups with Cl groups. So you can see that it's maybe not the healthiest kind of molecule you could be eating just because it's halogenated, and we generally don't consider those very safe. But there's all these OH groups around. It almost looks like a sugar. It's just our bodies can't process that. So that's why it's a very low calorie or no calorie sweetener, is because we can't metabolize it. Now, it's in very small quantities, so that's why it's possible that it's safe, but nobody really knows in large quantities or, long-term effects of eating this stuff. So I'll just tell you a story that Splenda was, I believe it was discovered as a kind of potential pesticide. So I think the story or legend goes that someone said, "Hey, taste this," and or test this, and they thought the person said taste it, so they tasted it and it was sweet. So that became a treat. It became sort of a sweetener. And here are some different kinds of sweeteners. People have also experimented with the idea of using L sugars instead of D sugars, because our enzymes only work with the D sugars mostly. So so there's some sweeteners based on that as well. But you can see many of the sweeteners are many times sweeter than sugar. So that means that you don't need as much of them in your drinks. So that's actually very, might be positive, right? That you have just a little bit of a really, really sweet aspartame, for example. But on the other hand, we don't know what that does in our body necessarily. So people are a little bit worried about what these different molecules do, because they're not natural. They're manufactured. So I hope you learned a little bit about carbohydrates, and I hope you enjoyed it, and we will start with amino acids next time.